Next, my topic is properties of eigenvalues and eigenvectors. Previous topic is we find eigenvalues and eigenvector. Here we see that properties of eigenvalues and eigenvectors. First property is sum of eigenvalues of a matrix is the sum of main diagonal elements. We adding all eigenvalues, we get sum of main diagonal elements. Our second property is product of eigenvalues equal to determinant of A. Third property is a square matrix A and A transpose have the same eigenvalues. Fourth property, eigenvalues of a triangular matrix are just the diagonal elements. Next property is if lambda is eigenvalue of A, then 1 by lambda is an eigenvalue of A inverse. Proof, if x be the eigenvector corresponding to lambda, our format is A minus lambda into x equal to 0. Here we write Ax equal to lambda x. Pre-multiply A inverse on both sides. A inverse Ax equal to A inverse lambda x. A inverse A equal to I. So we write I into x equal to lambda A inverse x. So we take lambda is opposite side. So multiplication going to opposite side, we write 1 by lambda. 1 by lambda I into x equal to A inverse x. So A inverse minus 1 by lambda I into x equal to 0. Hence 1 by lambda is the eigenvalue of A inverse. Next property, if lambda is an eigenvalue of an orthogonal matrix, then 1 by lambda is also its eigenvalue. Next property is if lambda is an eigenvalue of A, then lambda power m is an eigenvalue of A power m. M is a positive integer. Proof, given lambda is an eigenvalue of A and x1 is the eigenvector corresponding to lambda. Our format is A minus lambda into x equals 0. We write Ax equal to lambda x. Here we write this is equation 1. Pre-multiply A on both sides, previous equation 1. A into Ax equal to A lambda x. A squared x equal to lambda Ax equal to A. Already we know in equation 1 Ax equal to lambda x. Here we apply lambda into lambda x. We rewrite lambda squared into x. A squared x equal to lambda squared x by A squared minus lambda squared I into x equal to 0. But lambda squared is an eigenvalue of A squared. Similarly, we find m times lambda power m is an eigenvalue of A power m. M is a positive integer. Next, this is our problem based on properties. Find the sum and product of the eigenvalues. Our matrix is minus 2, 2, minus 3, 2, 1, minus 6, minus 1, minus 2, 0. Our sum is we find sum of eigenvalues and sum product of eigenvalues. Our property is sum of eigenvalue is equal to sum of main diagonal elements. That is our property 1. So here using that property we get the answer is minus 1. Next, product of eigenvalue is equal to determinant of A. Only here we find determinant of A, that is equal to product of eigenvalues. So our given matrix A, we find determinant of A solution is 45. So product of eigenvalue is 45. Next sum is the product of two eigenvalues of 6 minus 2, 2 minus 2, 3 minus 1, 2 minus 1, 3 is 16. Find the third eigenvalue. Already we know that product of eigenvalue equal determinant of A. So we find determinant of A is 2. So lambda 3 is 2. Third sum is 2 of the eigenvalues of 6 minus 2, 2 minus 2, 3 minus 1, 2 minus 1, 3 or 2 and 8. Find the third eigenvalue. Solution is lambda 1 plus lambda 2 plus lambda 3 equal to sum of main diagonal elements. Already we know that two eigenvalues, lambda 1 equal to lambda 2 equal to 8, 2 plus 8 plus lambda 3 equal to our sum of main diagonal elements. Our given matrix main diagonal is 6, 3, 3. Adding these three numbers we get 12. So 2 plus 8 plus lambda 3 equal to 12. 2 plus 2 is 10 plus lambda 3 equal to 12. So 10 is going to opposite side. Here, so lambda 3 equal to 12 minus 10, lambda 3 equal to 2. Next property is, if 3 and 15 are two eigenvalues of A, equal to 8 minus 6, 2 minus 6, 7 minus 4, 2 minus 4, 3. Product of we already we know that product of eigenvalue equal determinant of A. Here only we find determinant of A. Determinant of A is 0. So our lambda 3 is 0. Thank you.